Well, welcome back, freaks and weirdos. Let's do a little bit more of 4.3. We're about to wrap this thing up. You're probably thinking, thank God. When is this guy ever going to shut up? Never. I'm never going to shut up. Gonna keep talking. It's up to you whether you want to listen or not. All right. We're going to mess around with the second derivative test. We have a first derivative test already. And the first derivative test, we learn, hey, that's when we find local extrema. The second derivative test is going to do the same thing. It's just another method. Sometimes it's a little bit quicker and easier than the first derivative method. So let's see it. Let's just jump on down. And there it is, our second derivative test. So we're saying that, all right, so suppose we have a second derivative and this thing is, it's continuous on an open interval that contains some number that's just in the domain. So we're saying if you take a first derivative and it equals 0, right? That's a potential peak or a valley. That's what we were doing before with the first derivative test. Then we'd have to interval or do something like that. But now we're saying, well, if you just take a second derivative and plug in that same value of c, the same number, maybe that was like 7, I don't freaking know, and you find out that it's concave down, well, shit. So wouldn't the max hang out at the top of a peak where the slope of the tangent line would equal 0? So the derivative would equal 0. But isn't this concave down? Wouldn't all the water just fall right out of this thing? It is. So that's what we're saying. You take a first derivative, it equals 0, you plug the same damn number into the second derivative, and it's negative, then that's just concave down. We do it again. We look at this one. We're like, well, what if the derivative equals 0, but the second derivative was greater than 0? Well, it's a valley. It's just some sort of valley, right? Slope of the tangent line equals 0, but this shit holds water. There it is. It's a minimum. And then lastly, well, if the derivative equals 0 and the second derivative equals 0, it means do more work. You're going to go back to your first derivative test because this shit's just going to fail. So if that happens, you're like, nah, I'm getting the hell out of there. So let's do a problem. And you'll see this. Actually, they're not so bad. So let's go find the local min-max for, let's call it, I don't know, f of x, 2x cubed plus 3x squared minus 12x plus 6. And we're going to use the second derivative test. So what we have to do is take a first derivative and set it equal to 0 to start. So f prime of x is equal to, what do we got? 6x squared plus 6x minus 12. Oh shit, that better factor. So we're going to set this thing equal to 0 and solve. But first, do you mind if we just take a second derivative, just real quick, just underneath it? Like, what the hell? We're going to need to look at it anyway. So let's go through. That becomes 12x plus 6. Cool? Whatever. All right, so here's how our method works. We take this and we set it equal to 0. We can factor out that 6, and that leaves us with x squared plus x minus 2. And this becomes 6 times, what's that, x plus 2 times x minus 1 set equal to 0. Therefore, x is equal to negative 2, or x is equal to 1. That 6, of course, does not mean a damn thing for us. Cool. Now, if we want to know if they're local mins or local maxes, we just take them and we just plug them on in to f double prime. And we check it out. If the second derivative is going to be less than 0, then we must have a local max. It's kind of backwards there. So let's do the check. Let's look. F double prime of, and let's choose negative 2 first. Let's plop that one in. That is equal to 12 times plus 6, and that's a negative 2. We pop it in, and this thing is equal to, that's negative 24, so what's that? Negative 18. Therefore, we have a negative concavity. Negative concavity does this. So what does that say? Therefore, f of 2 is a local, what is that, min or a max when you sit on top of something? Max! We found it. This method is not bad. Now it goes through and we're like, well, let's check the other one out. F double prime of 1. We plug that thing in. We're like, well, that's 12 times a positive number plus another freaking positive number. This just becomes positive 18. Oh shit, so then that means this thing must be concave up. It must be holding water. Therefore, we must have down below. Therefore, f of 1 is a local, right? That's not a max, that's a min. It's the bottom of the bowl. And there we go. No big deal. Second derivative test. Well, let's try this one. Well, I'm going to give you just a second. Huh? Stuff. Hit pause. All right. Now let's play the game again. And we'll do this with f of x is equal to x to the fourth minus x cubed plus 2. Now this one will be a little bit more interesting. So let's just take a first and a second derivative. And when you start doing your graphing, that should just be your first step. When you do your 4.5 on your own, you just take derivatives first. Set everything equal to 0. Start solving. But we're going to go. What do we get? 4x cubed minus 3x squared. Oh, that's done. That's done. We don't need to do anything else there. And now let's just take a second derivative just to find out where we're at. And this becomes what? 12x squared minus 6x. Cool. Well, we could certainly find out what the derivative, second derivative equals 0. We don't give a shit about that. So we've just taken it. Now we're going to take our f prime of x and we're going to set it equal to 0 and we're going to solve. I think we can yank out an x squared, and this is going to leave us with 4x minus 3. Yeah, isn't that what it is? 4x minus 3? Is that what we got going on here? All right, cool. So we're going to take our x and we set it equal to 0. We're going to take our 4x minus 3 and we set that equal to 0. So we find out that we have x is equal to 3/4 and x is equal to 0. There's those two values. Now, the only thing we need to do is go plug that stuff on into our second derivative and find out what happens. So we're like, all right, cool. F double prime, let's plug our first number in. Let's go with 0. And we look and it's like 12 times shit. That's not going to tell us anything. That equals 0. So this tells us nothing. We would have to do some interval testing. That's this case up here. So it may have a local max or a local min, or maybe it's just nothing. It tells us nothing. We would actually have to interval test or graph it or do something like that. So we would want to use our first derivative test on that. So, well, let's go through and check 3/4. So f double prime of 3/4. We plug that shit in there. All right, cool. We get 12 times 3/4 squared minus 6 times 3/4. Now I know everybody's busting out their calculator, huh? No way we could ever do this without a calculator, right? So this is going to be what the 9 times 12. I don't know what that is. 108 over. 108 over, what's that going to be, 16, minus, what are we going to get, 18 over 4, so that's going to be 9 over 2, and 9 over 2, and then 108, and we're going to plug that stuff in, and what are we going to get out of this? I'm sorry I'm being a weirdo, I don't have a calculator with me at the moment, I didn't even think about having to do this, which one's going to be bigger, so 54 over 8, and we can probably cut that thing in half one more time, and we can get 27 over 4 minus 9 over 2. Oh shit, 27 over 4 is bigger than 9 over 2. You know how we can tell? We can just actually do this. Minus 18 over 4. Yay, it's positive. So we just found out that at 3/4, at f double prime of 3/4, it's greater than 0. So what does that mean? Doesn't that mean that we, oops, I didn't write that little, I didn't need that right now. If it's greater than 0, don't we have some sort of, it's holding water? We must be at some valley. Therefore, f of 3/4 is a local min. Now to mess around back again, because we still need to look at this thing, this x equals 0, we would actually have to have a little bit more information. So we would need to interval test, just like we had done before, taking a first derivative and plugging it into the interval and just see if it's positive or negative around the outsides of it. Or we could just go through and take a look at the graph. But if we were just to take this, we're right around 0. And we also have our 3/4, but we would just want to maybe plug in like a half and maybe -1, right? Interval testing, and this is for f prime of x, right? That interval testing. But I'm just going to pretend like we have the graph so we can look in at this. And here it is. We can see at 0. Here was our big issue that we had. We look to be, what's this? This is concave up, and then this is concave down. So it looks like we actually would have found out that we have, we don't actually have a, oops, I don't know why I'm talking about concavity. There's actually not a local min or a local max there, I don't know why I said this, so ignore the last like 30 seconds of the shit I was saying. We're not talking about the concavity, we're talking about local mins and local maxes. And this is clearly not a local min or a local max because it drops down, and it drops down again. So we would find out through this that this would be negative and negative just by doing our interval testing. I'm cheating just for the sake of time. So that f double prime of 0, that little case right here, it was absolutely nothing. It didn't give us something. The only answer we found out is that f of 3/4 is a local min. So be very careful. Wanted to make sure you could see this. When we have a second derivative equal to 0, it tells us absolutely freaking nothing. You need to go back to your first derivative test and do maybe some interval testing as such. Pop it up in Desmos and see that there was not a local min or local max there. We'll come back and we'll do a little bit of graphing. Fun. And we'll do it in a weird ass way, which will be one of your testable problems. I will see you soon.